We're going to take a look at our homework questions on 756, specifically question number 3. It says, what's the magnitude of the magnetic field that will stop ions from being deflected while they move at a speed of 75 kilometers per second through an electric field with a magnitude of 150 newtons per coulomb? First thing we want to deal with is that, right? Never want to be in kilometers per second. Never. Want to be in meters per second. It's a bit of an odd conversion, actually. When we see that, what do we want to do? What's instinct tell us? 75 kilometers per second converted to meters per second, divide by 3.6, right? Kilometers per hour to meters per second is divided by 3.6. What do you got to do to convert kilometers per second to meters per second? Multiply by 1,000. You already got seconds on the bottom. You got to convert kilometers to meters, and that's an easy one, right? Just multiply by 1,000. Okay, we want to stop these things from being deflected. Which section of the cathode ray tube are we dealing with here? By the way, I say the cathode ray tube. It's not really a cathode ray tube, right? We're talking about ions here as opposed to electrons. This is really what we call, and I probably would have mentioned this in the podcast yesterday that you guys watched, the mass spectrometer. Did I mention that? No? A mass spectrometer is a device that's like a cathode ray tube, except it uses ions as opposed to electrons. And the purpose of a mass spectrometer is often to identify what the ion is. So essentially, we fire the ion through this thing that's like a cathode ray tube, we measure its properties, and then we determine what it is based on its properties. So that's what we got here. We analyze it in the exact same way, though. It doesn't change a thing, except the charge isn't necessarily the charge of an electron, and the mass isn't the same. Which section of the cathode ray tube or mass spectrometer are we dealing with here? In which section do we stop ions from being deflected? In other words, let me rephrase it. In which section do ions go undeflected? Or straight through, Joseph? Yeah, the middle one. We call it the velocity selection chamber. It doesn't matter what you call it, really. Okay, if you know what you're talking about, whether you don't remember the name or not is not a big deal. In the middle section, the velocity selection chamber, we say Fe equals Fm. The upward electric force equals the downward magnetic force. We'll say Q times E is equal to QVB. Neither one of those equations are new, right? Putting them together is new. Q's cancel because it's the same charge. We're solving for the magnetic field, so B will be equal to E, the electric field, over the speed. That's 150 newtons per coulomb, and we divide that by the speed of 75,000 meters per second. And when we do that math, I assume we get the answer in the book, 2.0 times 10 to the minus 3. That make sense? Is 10 to the minus 3 a reasonable magnetic field? Sure it is, right? The magnetic field caused by the Earth is about 10 to the minus 5. A typical bar magnet typically would be 10 to the minus 2. Hey, is that reasonable? Yeah, 10 to the minus 3 fits in there. If you get something that's 10 to the positive 4, you're wrong, because you won't get a magnetic field on Earth that's 10 to the 4 Tesla. It's just too big. The second one we wanted to go over was page 758, question number 3. It says a carbon-12 ion. So again, we're dealing with a mass spectrometer, not a cathode ray tube, but the analysis is the same. A carbon-12 ion has this charge to mass ratio. We want to find the radius of the ion's path when it travels 150 kilometers per second, again, perpendicular to a magnetic field. Which section of the cathode ray tube or mass spectrometer are we dealing with in question number 3? Again, names, I don't care about the name. Okay, as long as you can tell me section 1, 2, or 3, that's good enough. Where's the only section where the charged particles go in a circle? It's got to be section 3, right? I call it the main chamber, although that's not really the official name for it. Section 3. In section 3, we say Fc equals Fm. Bottom line is this. If the question talks about the charged particles speeding up, it's the first chamber. If it talks about it going through undeflected, it's the second chamber. If it talks about it going in a circle, it's the third chamber. That's what we got here. going in a circle, the third chamber. MV squared over R equals QVB. One of the V's cancels, left with MV over R equals QB. And now we want to solve for not Q, not M, but Q over M. Now, some of you might say, well, why don't we just solve for R? Okay, let's try that. Let's try solving for R, since that's what we're looking for, right? R goes up by multiplying, QB goes down by dividing, it becomes MV over QB. What's the issue with that? It's correct, but what's the issue with that when we're trying to solve this question? Yep. We don't know what Q or M is. We know what Q over M is. This equation has not Q over M, but M over Q, right? If we do this, if we rearrange it to solve for Q over M, M goes down, B goes down, V over B times R, and we sub in the value for Q over M here, 8.04 times 10 to the 6. That's not Q or M, it's Q over M, equals 150,000 meters per second, divided by B, 0.50 times R. Well, now we can find R, right? R goes up, 8.04 goes down. Just trade places there, right? And I assume when we do the math there, it works out to be the answer that's in the book, 0.037 meters. Is that okay? Who asked me for that one? Is that good? The alternative could have been, when I rearranged this to solve for R, right, I got MV over QB. I don't know what M over Q is, but if I know what Q over M is, what could I have done? I could have inversed it, yeah. I could have taken that number, 8.04, and flipped it over, right? X to the minus 1, and got the number for that. Okay. Whatever's less confusing to you is what you should do. All right. All right, if we're good with the discovery of the electron and the calculations that go along with the discovery of the electron, now let's figure out some more information about that electron, right? Not just Q over M, the charge to mass ratio. Let's figure out, how about the charge and the mass instead of the ratio of the charge to the mass? So we're going to fast forward a few years to a guy named Robert Millikan, who performed an experiment called the oil drop experiment. This is probably, there's no doubt about this actually. When I performed this experiment in university, in a class, my third year university, was the class that was purely lab, 6 hours a week of lab. Sometimes the lab, good news is sometimes the lab took 2 hours and your 6 hour class was a 2 hour class. 6 hours by 3 hour sessions a week. But then sometimes your 6 hour lab would take you 9 or 10 or 12 hours and so on. This one was, I hated this one with a passion. This one took the longest, it was the most difficult, it was the messiest of any experiment I have ever done. The oil drop experiment involves this. 2 metal plates, attached to a battery. Actually, we're going to switch that battery around, although it doesn't really matter. You'll see why in a few minutes. With the way the battery is set up right now, this top plate would become positive, and the bottom plate would become negative. That seems easy enough. So what happens next? You guys, if you have cologne or perfume in the bathroom at home, you spray it, right? It's this liquid, and it comes out into these tiny little droplets, tiny little particles. Millikan would use something similar to that with the oil that he had. He would have had oil inside this thing that he called an atomizer, and when he squeezed the little thing in the atomizer, it came out like perfume comes out of a perfume dispenser. It makes these particles of oil It's really, really small. Now, we call it an atomizer. We don't mean that he literally made these drops of oil into the size of atoms. They were much bigger than the size of atoms, but they were really, really small, just like perfume or cologne particles are when you press that button on the perfume dispenser. These oil droplets would have went in between these plates. Some of these oil droplets would have been negatively charged, and some of these oil droplets would have been positively charged. Why? Well, there's a couple of reasons. One, because these oil droplets, as they're leaving the atomizer, they rub against each other, and they rub against the nozzle of the atomizer, so they charge by friction. Some become negative, some become positive. In addition, he would have ionized some of these particles to give them a charge, right? To purposely give them a charge. Doesn't really matter so much for us, though, how they got the charge. The main thing is that some of these oil droplets were negatively charged, some of these oil droplets were positively charged. I want to focus now on the negatives and the positives and what forces act on the negatives and positives. There are two forces that act on each of them. I'll give you a hint for the first one. The first one always acts on these charges, always in the same direction, and it always acts on everything else, not just these charges. What would it be? Gravity. Gravity acts down on both of these charges. Now, I don't know if anybody thought this yesterday when you were learning about the cathode ray tube, especially when you're going through the velocity selection chamber where you had an electric field and a magnetic field, and we say these particles went straight through because the electric force equaled the magnetic force. Anybody think about gravity there? Where does gravity come into play? Well, it does act on them. Gravity does act down on these electrons as they go through the velocity selection chamber, but because we're talking about electrons, literally, tiny little electrons, the force of gravity on them is so ridiculously small that we don't have to pay any attention to it with the velocity selection chamber. We do with the oil drop experiment because we're not talking about electrons. We're talking about oil droplets. They're really small, but they're still much, much, much more massive than an electron is. So the force of gravity matters now, whereas it didn't matter yesterday when you did the cathode ray tube. What other force do you have acting on these particles? Think about this. What other force do we have acting on these positive or negatively charged particles? An electric force, not a magnetic force, an electric force, which acts downwards on this one, away from the positive, and it acts upward on this one. Now, I haven't drawn those forces to scale. One force could be bigger than the next, or they could balance each other out, but bottom line is, sorry, that's backwards, isn't it? I just saw the look on Grace's face. The electric force is upwards on this one and downwards on this one. Is that right, Grace? Good, thank you. Again, the values of them, we don't know. Which one's bigger? We don't know yet. Okay, we're just drawing them in the right direction right now. I want to focus right now on this particle. In fact, not just on this particle, but a specific case of this particle. Keep in mind as we're going through this the whole time, we haven't mentioned any electron yet. We're talking about oil drops. But remember the purpose of this? The purpose of this was to find the charge of an electron. Okay, we're not close to being there yet. Okay, but if you understand what we've said so far, good, you're on your way. So I want to focus on this negatively charged oil drop, not an electron, but an oil drop with a mass that's much bigger than the mass of an electron. In fact, I want to focus on that specific case where those two forces, Fe and Fg, are the same. They balance. Sometimes Fg might be bigger, sometimes Fe might be bigger. Let's not worry about that right now. What happens when they're balanced? What happens when those two forces are equal? One of two things. If the particle is at rest, it's going to it's going to stay at rest. It's going to be suspended. If the particle is moving, it's going to keep moving at a constant speed. So for the particles that are either suspended or traveling at a constant speed, we know the upward electric force must equal the downward gravitational force. Don't get that mixed up with the velocity selection chamber of the cathode ray tube, where Fe equals Fm. Here it's Fe equals Fg, or Q times E equals M times G. Typically what you do here is solve for charge. Get mg over E, gravitational force over the electric field strength. Charge of what? The charge of the, good, the charge of an oil drop, not the charge of an electron, the charge of an oil drop. We're getting there. Still not there yet, but we're getting there. Millikan would have performed this experiment hundreds of times. He would have gotten the charge on hundreds of different oil drops. And he would have found that the charges might equal something like this: 3.2 times 10 to the minus 18, 6.4 times 10 to the minus 19 coulombs, 1.6 times 10 to the minus 17 coulombs, 1.6 times 10 to the minus 19 coulombs, 4.8 times 10 to the minus 17 coulombs, and so on. What do you notice about all those charges? What do you notice about the charge of each of these oil droplets? They're all multiples of this number. Okay, this one is 20 times this one. This one would be 4 times. This one would be 100 times. This one would be 400 times. They're all exact multiples of this number that we now call the elementary charge. So what's its conclusion? There is an elementary charge. The smallest possible charge, 1.6 times 10 to the minus 19 coulombs. You can't get smaller than this charge, Millikan says. Well, if that's the smallest charge we have, then that must be the charge of this electron that Millikan discovered. Look at that. Thomson discovered. Thomson discovered the electron, found the charge to mass ratio of the electron. Millikan said, hey, I know more than that. I know the charge, not just the charge to mass, but the charge itself. It's the elementary charge. It's 1.6 times 10 to the minus 19. How do I know that? Because all these oil drops I measured the charge of were multiples of this one number. He also, by the way, his second conclusion was the charge is quantized. What does that mean? Money is quantized. Money is quantized. In Canada now, you can have 5 cents or 10 cents or 15 cents or 20 cents or 25 cents. Can't have anything in between, right? You can have an elementary coin, which would be a nickel, or a whole number multiple of that. Money is quantized. So is charge. You can have an elementary charge or a multiple of that, but you can't have anything in between. You can't have 1.7 times 10 to the minus 19. You can have 1.6 or 3.2, but nothing in between. Just like you can have 5 cents or 10 cents, but nothing in between in Canada. So we discovered the elementary charge or the charge of the electron, and he discovered that charge is quantized. So here we have a problem where an oil drop, not an electron, but an oil drop, is suspended. Okay, this is a good thing because we know how to deal with this when the oil drop is suspended. In an electric field of this value, how many electrons has the electron or the oil drop gained or lost? How many electrons? Okay, let's deal with that in a minute, okay? Right now, let's just say we want to find the charge. What's the charge of this oil drop? Here's the mass. It's suspended. That's good. Here's the electric field. I'm going to circle this in red, actually, because the direction of that is important. You'll see why in a minute here. We know that when it's suspended, we're going to set Fe equal to Fg. Almost said Fe equals Fm. Okay, just caught myself at the last second there. Okay, that would have been the velocity selection chamber of the cathode ray tube. It's not what we do here. QE equals mg. Q equals mg over E. All right, I can find the charge now. We do that, we get 8.0 times 10 to the minus 19 coulombs. How many electrons would that be? Yep. 5. How do you know that? Yep. Yep. You're going to say the total charge divided by the charge of one electron equals 5. So Tiffany goes to the store and buys a bag of oranges. Each orange weighs 100 grams. She doesn't know how many oranges she has. She weighs the bag of oranges. It weighs 600 grams. How many oranges does she have? 6, right? We take the total mass of the bag divided by the mass of one orange. We say she's got 6 oranges. We can all figure that one out. This is no different except that we're dealing with numbers that are a little bit trickier because there's exponents. The total amount divided by the amount for 1. We get 5 electrons. Gained or lost? Ooh. Gained or lost? Is it 5 electrons extra that we have now or 5 electrons fewer that we have now? Whenever you're dealing with that, pay really close attention to this because I know when I'm walking around and you guys are working on problems, people are going to have questions with this. So pay close attention so that you at least get as much as you can. Please draw a picture in a case like this. You don't even have to draw the plates necessarily. Draw what you know. The electric field is downward, right? The particle, if it's suspended, the particle must experience a force of gravity down, and to be suspended, it has to equal an electric force up. Otherwise, it wouldn't be suspended, right? If they were both forcing down, it wouldn't be suspended. What kind of particle experiences an upward electric force in a downward electric field? Is it a positive or a negative particle? Got to be negative. Because a positive would experience an electric force in the same direction as the field. If it's a negative oil drop, then that must mean it gained 5 electrons. If it was a positive oil drop, it must have lost 5 electrons. Okay? It's not crazy hard, but some of you will still struggle with that. Draw the picture, and it starts making a lot more sense when we draw that picture. Let's try page 763 for the next few minutes, please. Take a look at number 2 here. It says, what electric field will suspend an oil drop with a mass of 3.2 times 10 to the negative 14 kilograms and a charge of plus 2 times the elementary charge? We've seen this notation before, right? 2e on your data sheet. In fact, it says the charge of an electron is negative 1e. When we go back to our data sheet, it says an e is an elementary charge. Now we know what an elementary charge is. It's the smallest possible charge. So, of course, an electron is negative 1 times the elementary charge. What electric field will suspend that? If we're talking about suspending, then we know that Fe must equal Fg in the context of the oil drop experiment. So we're going to say Q times E equals M times G. we're going to say E is equal to mg over q. So we're going to say 3.2 times 10 to the minus 14 times 9.81 over 3.2 times 10 to the minus 19. What do I get there? I assume 9.8 times 10 to the 5. Okay, but that doesn't tell us whether it's up or down. Yep. Yep. Oh yeah, absolutely. Absolutely will. Everything we do, you can see on the diploma, right? 9.8 times 5 meters per coulomb, but it doesn't say up or down in the equation. Just because it's positive doesn't mean it's up. The equation is not going to tell us up or down. So how do we figure that out? We draw a picture. We say that it's a positively charged particle. And a positively charged particle must experience an electric force, gravity force down and the electric force up. If it's going to be suspended, those two forces have to balance. If it's a positive particle and it experiences a force upwards, then what direction does the field have to be? Positive particles experience an electric force in the same direction as the field. So, if it was a negative particle with an electric force upward, then the field would have to be downwards. A positive particle, the electric field has to be upwards because it's always in the same direction as the force. Right? Last little burp here. What do we do if the charged particle isn't suspended? What do we do if the charged particle is moving? Well, it's the same thing. If it's moving at a constant speed, same thing as we just did. What do we do if it's accelerating? If it's speeding up or slowing down, upwards or downwards? That could be a situation where the negative particle experiences an electric force like this and a gravitational force like this. Even though they're opposite to each other, they're not balanced. Or it might be a situation where the positive particle experiences a gravitational force like this and an electric force like this downwards. Anyway, you look at it, in these questions, the forces aren't going to balance. It's going to cause it to accelerate either up or downwards. By the way, which way would this one accelerate, up or down? Yep, upwards. We don't know how fast. Could accelerate upwards at 3 meters per second squared or 15 meters per second squared. Fe is bigger than Fg, so it's going to accelerate upwards. Which way does it accelerate this way? Downwards, right? At what rate? 3.5, 9.81, 15? More than 9.81. Because with just gravity, it would be 9.81. But with both of those, it's got to be bigger than 9.81. What about this one? While we're at it. It's going to accelerate downwards, right? Because Ft is bigger. At what rate? Something less than 9.81. Because you've got an upward force countering gravity. Okay, anyway you look at it, all three of these cases. Oh, you know this. I'm not going to write this down. What comes next? We've done this all through Physics 20 and a number of times in Physics 30. What comes next? Yeah. You say m times a, but even before that, we usually say something else equals F net first. When there's more than one force acting. Yeah. We're going to say Fg plus Fe, the sum of the forces. And then, Sam, we usually set that equal to m times a, unless we're just looking for the net force. Notice I haven't plugged in any signs yet, right? The signs come when we plug in numbers. Okay, so for this one, well, for all three of them, Fg will be negative. But the electric force, QE, well, it's positive here, it's negative here, and it's positive here. MA, positive or negative? Well, it'd be positive here because it accelerates up, negative here, and it would be negative here because it accelerates downward. Once again, the diagram comes in handy. Figure out which way each of these forces, including the net force, is acting. This one is always negative. These ones can be positive or negative, depending upon the circumstances. Typically, you do the same thing. Get the charge of the oil drop, and then what do you do with it? Now you repeat it 100 times. Find that the charge is always going to be 1.6, or a whole number multiple of 1.6. We draw the same conclusions. It's just a slightly more complicated analysis to get that, that's all. Let's take a look at this one, our last example of the day here. A tiny plastic sphere. When you perform this experiment in high schools, and some people do actually perform this experiment in high schools, we don't, because it's very expensive. The equipment you need is very expensive. And in the end, you probably end up getting one of them because it's so expensive. But when you do it in high schools, typically you don't use foil. You use a plastic sphere or a latex sphere. That's much, much, much less messy. And it works pretty good, actually. So you got a plastic sphere of this mass being placed in an electric field that's downwards, has 10 excess electrons. Will it accelerate, and if so, which direction? So it's an oil drop experiment, except, well, I'll call it a plastic sphere drop experiment. Is it going to accelerate? Well, let's find the acceleration and see. Draw a picture to figure out directions here. The electric field is downwards. The sphere is negative 1.6 times 10 to the minus 18 coulombs because it has 10 excess electrons. If it's a negative particle in a downward field, the electric force has to point which way? Negative particle, downward field. The electric force points upwards, opposite to the direction of the field for a negative particle. Gravity points downwards. So let's say FE, F net, equal to FE plus FG. We're not worrying about directions yet. Now let's plug in some numbers and worry about directions. M is 8.2 times 10 to the minus 15 times A. That's really what we want to find here, right? Does it accelerate? Well, if A is 0, the answer is no, it doesn't. If A is something, then it accelerates. Let's worry about signs. We don't know which way it accelerates, right? We do know which way gravity acts. It acts downwards, so let's make gravity negative. What about the electric force? Electric force, positive or negative? Jeremy, which way does the electric force point? So it's going to be, despite the field being downwards, we care about the direction of the force. It's upwards, so it points, so we're going to make it a positive value. So what you're going to want to do now is get the number on the right-hand side. We'll do that as a group here. And then simply divide it by 8.2. So 1.6 times 10 to the minus 18, not 19, times 1 times 10 to the 5. Add that to, subtract from that. Use some brackets here. 8.2 times 10 to the minus 15 times 9.81. And now let's divide that by 8.2. We get 9.70. Two digits should be 9.7. Does it accelerate up or down? Jen? How do you know? How do you know? How do you know that without having calculated electric field or gravitational force? Sorry, electric force or gravitational force. Okay, how do you know that the electric force is bigger? Good. Good. You got a positive acceleration, which means it accelerates upwards. So the electric force must be bigger than gravity. Quite a bit bigger, actually, right? Because you've got a pretty big acceleration there. Yeah. See how the picture helped again? And these questions tend not to be that difficult unless you don't draw pictures. When you don't draw pictures, some of these become tricky. Draw the picture and remember two things. Positive particles experience a force in the direction of the electric field. Negative particles experience a force opposite to the direction of the electric field. Remember those two things, draw your picture. You should be able to get any direction or any positives or negatives or anything you're dealing with. Yep. Good question. How is this charge 10 to the negative 18? Where did that come from? I kind of went through that a little quickly, actually. Isn't it 1.6 times 10 to the minus 19? Raise your hand up there. Yeah, it's 10 extra electrons. So if the charge of an electron is 10 to the minus 19, 10 of them would be 10 to the minus 18. Okay, good? All right, let's see what you're going to do with those two questions over the next couple minutes here.